Hello friends, welcome to the channel. Today we are going to deal with the chapter nuclear physics. Let's start. So now as you can see, I have written the definition of nuclear physics. First of all, the branch of physics which deals with the study of nucleus is referred to as the nuclear physics, and the discovery of the nucleus was performed by the scientist Rutherford. Now you can see the diagram of a nucleus here. You can see these positive charges, these are the protons, and these empty holes, I would say, these holes, I would say, they are chargeless. They are basically the neutrons. Now see, the discovery of nucleus was performed by Rutherford. The discovery of neutrons was performed by the scientist Chadwick, and these are the protons, and the protons were discovered by the scientist Goldstein. And the complete sphere, this complete sphere which you can see is the nucleus, which was discovered by scientist Rutherford. Let's move ahead. Now see, let me also tell you the mass of neutron and the mass of proton. Now in various books it is shown that they are nearly equal, but let me tell you an interesting fact that the mass of neutron is considered to be slightly greater than the mass of proton, because the mass of neutron is near about 1.6749286 into 10 to the power minus 27 kg, while the mass of proton is 1.6726231 into 10 to the power minus 27 kg. So now let me tell you the representation. See, this is, let us consider this X to be an atom, and Z the atomic number, and this A as the mass number. So let me also tell you that this X represents an atom, Z is the atomic number, and the A is the mass number. Or we can say this to be equal to the number of nucleons. Now nucleons is the combined term which is used for the protons plus the neutrons together. Protons plus neutrons together constitutes the nucleons, right? Now let me tell you some common terms, such as the first one is isotopes. See, these isotopes, let me tell you the definition of isotopes: the nuclei which are having the same number of protons, the nuclei which are having the same number of protons but the different number of neutrons. That means in case of your isotopes, the protons will be same but the neutrons will be different. Now coming to isotones. See, isotones, the nuclei having same number of neutrons. That means in case of isotones, the neutrons are same in number, while the protons are considered to be different in number, just opposite to that of isotopes. Now moving further, see, another term we have isobars. See, the isobars, the nuclei having same mass number, having same mass number but different atomic number. but having different atomic number. Now there is a relation for the radius of nuclei, that is r is equals to r naught into a to the power 1 by 3. Here this r represents the radius. R naught is a constant. See, the value of r naught is near about 1.13 into 10 raised to the power minus 15 meters. Or what we can write it to be equal to 1.13 Fermi, because 1 Fermi is equals to 10 raised power minus 15 meters. Now here A is the mass number, right? Now there is a value of density also given for nucleus. The density of nucleus. See, the density of nucleus is equal to near about 3 into 10 to the power 17 kg per meter cube. The value of density of nucleus is near about 3 into 10 to the power 17 kg per meter cube. Now we have the definition of the atomic mass unit. One atomic mass unit, that is 1/12 the mass of C12, carbon 12 atom. It is 1/12 the mass of carbon 12 atom at rest in its ground state. In its ground state. Now let me also tell you an interesting fact, that the mass of proton is nearly equal to the mass of neutron is near about equal to 1 atomic mass unit. You should remember this, because ahead when we'll be solving some questions, then it will be very useful. We have a question now which says that calculate the radius. We have to calculate the radius of germanium having the mass number to be 70. Now we can use the relation r is equal to r naught into a to the power 1 by 3. You can take the answer in Fermi. See, r is equal to, as you know, 1.13 Fermi into 70 to the power 1 by 3. Now this will nearly be equal to 1.13 into 4. That means the answer will nearly be equal to 4.5 Fermi. Or we can write that the answer is near about equal to 4.5 into 10 raised to the power minus 15 meters. This is the answer in meters as well as in Fermi. Right? Now, I'll tell you the mass defect now. Now see mass defect, which is also represented by delta M, the symbol delta M. Now see, it is observed that there is a difference, in expected and the actual mass of nucleus, and that difference is the mass defect. Let us see now. Let us consider, suppose the expected mass is atomic number Z into the mass of proton plus A minus Z into mass of neutrons. Now you can see these are the number of neutrons, as this is the mass number subtracted by the number of protons or the number of electrons will give us the number of neutrons. So these are your number of neutrons. So like this we have calculated the expected mass. Now let us see the observed mass. See now, observed mass is mass of the complete atom minus atomic number multiplied by the mass of electrons will give us the observed mass. Now, what does the mass defect says? Delta M. What does the mass defect says? Delta M. That is expected mass minus the mass that is observed. Delta M is equals to atomic number multiplied by the mass of protons plus A minus Z, that is the number of neutrons as I stated here, A minus Z into the mass of neutrons minus the mass of atom, this one, mass of atom minus Z into the mass of electrons. This is the way how we calculate the mass defect, as you can see. By this we calculated the mass defect. Now we will continue with the binding energy concept and further in the next video. Thank you.